Welcome back, fellow tech warriors. This is Lab 404, signing on. For today's mission, we're installing the core devices that keep systems alive. You got power, cooling, storage, memory, and CPUs. These components determine whether a system runs smoothly or fails under load. Now, let's begin. First off, we've got power supplies and cooling. The power supply unit, or PSU, is responsible for converting household AC power into regulated DC voltages used by computer components. Inside of a power supply unit, you have many components. You have things like a rectifier that converts AC power to DC, transformers to step voltage down, you have voltage regulators and filters to smooth output, and a cooling fan to dissipate heat. Without stable power delivery, no system can operate reliably. Next, we have PSU compatibility requirements. A PSU must be compatible with the case form factor, the motherboard connectors, and the input voltage. Low line power ranges from 100 to 127 volts. High line power ranges from 220 to 240 volts, and many modern power supplies are auto switching, but older units may require manual voltage selection. You also have things like wattage rating and power distribution. Power is measured in watts, calculated as volts times current. When selecting a PSU, you have to consider CPU power draw, GPU power draw, drives and peripherals, and future upgrades you may need. The 12-volt rail is especially important in modern systems because CPUs and GPUs draw most of their power from it. An underpowered PCU can cause random shutdowns, system instability, or permanent hardware damage. Typical wattage ranges include 400 to 500 watts for standard desktops, 600 watts or more for gaming and workstations, and 1000 watts or more for servers. Next up, PSU efficiency, the 80+ ratings. Efficiency measures how much incoming power is converted into usable output. Higher efficiency reduces wasted heat, lowers electricity costs, and improves long-term reliability. 80+ certification levels include bronze, silver, gold, platinum, and titanium. The higher the rating indicates better efficiency under load. Next up, power connectors. Common PSU connectors include 20 and 24 pin motherboard connectors. You have 4-pin or 8-pin CPU power. You have PCIe power connectors for graphics cards, SATA power connectors, and Molex connectors for some legacy devices. Many power supplies use the 20 plus 4-pin connectors to maintain backward compatibility with older motherboards. Now, let's talk modular and redundant power supplies. Modular power supplies use detachable cables which improve cable management, airflow, and ease of installation. You also have redundant power supplies which are used in servers to maintain uptime. If one PSU fails, the other continues supplying power. Redundant systems often support hot swapping, meaning failed PSUs can be replaced without shutting the system down. Now let's talk about cooling. All active components generate heat, and when you have excessive heat, it can shorten the lifespan of components. Cooling solutions fall into two main categories. You have air cooling and liquid cooling. Proper cooling is essential for stability and performance. First up, air cooling. Air cooling relies on heat sinks, thermal paste or pads, and fans to move air throughout the chassis. Thermal paste fills microscopic gaps between the CPU and heatsink to improve heat transfer. Dust buildup reduces cooling efficiency and must be managed through regular maintenance and cleaning. Next, we have liquid cooling. Liquid cooling is used in high-performance systems. Open-loop systems include a pump, tubing, water blocks, radiators and fans, and a coolant reservoir. Closed-loop or AIO coolers are sealed units that require minimal maintenance and are commonly used for CPUs. Now, next up, storage devices. You have volatile versus non-volatile storage. Storage devices fall into two main categories. Volatile storage, such as RAM, which loses data when power is removed. You also have non-volatile storage, such as hard drives, and solid-state drives, which retain data. First, let's talk about hard disk drives, or HDDs. Hard disk drives store data on spinning magnetic platters. Some of the key characteristics are large storage capacity, lower cost per gigabyte, mechanical components, and slower performance. Some common form factors include the 3.5-inch drives for desktops, The 2.5-inch drives for laptops and external closures. Performance is influenced by RPM, seek time, and access time. For the next main storage device, you have solid-state drives, or SSDs. SSDs store data using flash memory and contain no moving parts. Some of the advantages include faster read and write speeds, lower latency, and better shock resistance. Some key considerations include a higher cost per gigabyte and limited write cycles managed through wear leveling. Some of the common interfaces include SATA SSDs, PCIe and NVMe SSDs, and M.2, which is a form factor, not an interface. Next up, we're diving into RAID overview. RAID combines multiple drives into a single logical volume. It's important to note that RAID is not a backup. Drives should be identical, and RAID can be hardware or software based. Some of the common RAID levels are RAID 0, which involves striping to improve performance, but has no fault tolerance. RAID 1, which is mirroring, has fault tolerance, but typically reduces the usable capacity. You also have RAID 5, which is striping with parity, RAID 6 with dual parity, and RAID 10 with striping and mirroring combined. Next up, we have removable and external storages. External storages include external hard drives and solid-state drives, NAS devices, USB flash drives, and memory cards. SD cards vary by speed class, UHS rating, and capacity type. Now, we have optical drives. Optical media types include CD, DVD, and Blu-ray. Some common formats include recordable or rewritable. Optical drives connect via SATA internally or USB externally. Next, let's dive into system memory, some of the RAM fundamentals. RAM stores active data and instructions for the CPU. Some of its key properties are it's volatile, faster than storage, and it's measured in gigabytes. Some of the addressing limits for 32-bit systems support up to 4 gigabytes, but with 64-bit systems you can support significantly more. Now, you might be curious to how much more. Well, 64-bit addressing can support up to 2 to the 64 bytes, which is equal to 16 exabytes, or 16,000 petabytes, which is about 18.4 quintillion bytes. Now, that's a lot of bytes. That's up to 18 zeros following 18.4. Now, RAM can come in all different sizes and types. These are known as DDRs. Most modern systems use the DDR SD RAM, which is DDR3, DDR4, and DDR5. Now, DDR generations are not physically compatible due to notch placement. Performance is measured using MTs per second, or megatransfers per second. You also have cache latency and timing values. Now, there's different types of memory modules. Memory modules include DIMMs for desktop and SODIMMs for laptops and compact systems. Modules must match motherboard requirements for DDR generation, voltage, and supported speeds. Now, with multi-channel memory, it improves bandwidth. You have single channel, which offers 64-bit, or dual channel, which offers 128-bit, but there's also triple and quad channel, which are usually used in higher-end systems. Dual channel requires a matched memory module installed in paired slots. DDR5 introduces dual 32-bit subchannels per DIMM. Next up for memory, we have ECC memory. ECC memory detects and corrects single-bit errors. It's used in servers and workstations. It requires motherboard and CPU support. ECC and non-ECC modules should never be mixed together. Now, we're going to dive into the CPU with some CPU core fundamentals. The CPU executes instructions using cycles. You got fetch, decode, execute, and write back. Some of the internal components include registers, cache levels 1, 2, and 3, and ALU and FPU. ALUs, or arithmetic logic units, handle integer math and logical operations. FPU, or floating point units, handle decimals, or floating point math. Now, CPU architectures. There's two common types of architectures. You have CISC, which is used by 86 and 64-bit processors, and RISC, commonly used by ARM processors. CISC is complex instruction set computing, used by both 86 and 64-bit processors. It can handle large complex instruction sets and has fewer instructions per program, more work per instruction. RISC, or Reduced Instruction Set Computing, is commonly used by ARM processors, usually handling smaller, simpler instruction sets and more instructions per program, allowing for faster and more efficient execution. Next up, CPU sockets. Some common socket types include Intel's LGA, or Land Grid Array, and AMD's PGA, or Pin Grid Array. AMD is also coming out with some newer LGA designs. Some considerations you might keep in mind with installation is socket compatibility, proper thermal paste application, and secure cooling installation. Improper installation can result in overheating, system failure, or breaking components. Now we finally reached the end. Some key things to keep in mind before closing your system is verify compatibility, always use ESD protection, match PSU wattage to system load, maintain airflow and cable management, and document all changes. That's mission complete. This is Lab 404, signing off, and I'll see you next time in the next system breakdown.